So let's start with the new PML, discussion on new PML. So PML actually was analyzed using the stress coordinate system. We have defined a stress coordinate system for the PML layer, and del stress for the stress coordinate system will have extra terms here, which are called scale factor Sx, Sy, and Sz. Del operator is defined like this, and with the new stress coordinate system, we actually write the source-free Maxwell equations for the stress coordinate system. Curl of E is equal to minus j omega mu h. Only thing is that we'll take del operator in the stress coordinate system, and del operator is defined like this with the new scale factors Sx, Sy, and Sz. So now for this Maxwell equation in the stress coordinate system, you can actually find out the components of the curl operation. No? Curl operation, this, let's say you consider this first equation, curl of E is equal to minus j omega mu h. Only thing is del is stress now. Because of this, I can decompose this equation into three components. One for the x, one for the y, and one for the z components. So for the x component of the first Maxwell curl equation, you can write the equation like this: 1 by sy del iz by del y minus 1 by z del sy by del z is equal to j omega epsilon ex. So let us try to look closely what this equation does. We actually want to work in the time domain. So all the Fdtd equations are always in the time domain. So if we want to see this equation, you look at this equation, this is in the frequency domain. You can easily observe it because you see there is a j omega term here in the right hand side. This is actually for the phasor form or spectral domain or in the frequency domain. So we are in this frequency domain. This Maxwell equation is in the frequency domain because you have a j omega term here. So if you want to work in the time domain, which is for the Fdtd equations to work properly, you have to go in the time domain. So if you want to go back to the time domain from the frequency domain, as you know that in the Fourier transform, multiplication in the frequency domain will be converted into convolution in the time domain. So this parameter and this parameter in the time domain, they will be doing convolution. So Sy will be doing convolution with this del iz by del y. Similarly, this term here, which was multiplication in the frequency domain, will become convolution in the time domain. One this term here, convolution with this. We should actually define this term sy with the bar is basically Fourier inverse of 1 by sy, and sz with the bar is basically Fourier inverse of the 1 by sz. So this will be convolution in the time domain. This is also convolution in time domain, and the j omega term in the time domain will become del by del t. So you have epsilon del ex by del t. Okay, so let us look at the inverse Fourier transform of 1 by sy and 1 by sz. So let us look at the inverse Fourier transform of 1 by sx first. Then we can similarly do it for 1 by sy, 1 by sz also. So what was 1 by sz? What was 1 by sx? Sx was defined as kx plus sigma x by j omega epsilon. We have already added one extra term here, which is alpha x, so that we can define the breakpoint frequency based on the alpha x. So now you multiply by this term here, and in the numerator also finally you have 1 by sx will be alpha x plus j omega epsilon divided by alpha x kx plus j omega epsilon kx plus sigma x. So this term again you can simplify it. 1 by sx you can express this whole term like 1 by kx minus 1 by bx, where 1 by bx is this is a simple derivation, you can do it, and 1 by bx turns out to be sigma x by kx 1 by alpha x kx plus j omega epsilon kx plus sigma x. So we have expressed 1 by sx in the form 1 by kx minus 1 by bx, where 1 by bx is like this. Similarly, you can do it for 1 by sy. Also, 1 by sy can be expressed as 1 by ky minus 1 by by. 1 by sz can be also expressed as 1 by kz minus 1 by bz. So in a very contract form, I can write this 1 by si, where I is going from x. I could take value as x, y, or z. So In the general expression we have is 1 by Si is equal to 1 by Ki minus 1 by Bi, where 1 by Bi is equal to sigma I by Ki, 1 by alpha I Ki, j omega epsilon Ki plus sigma I. If you just substitute x here, it will be the expression for 1 by Sx. If it is substitute I as y, then it will be expression for 1 by Sy. If you substitute I as z, then this will be expression for 1 by Sz. So we have the inverse, this relation from here, you can find out the inverse Fourier transform of this. So if you want to take the inverse Fourier transform of this, Fourier inverse of 1 by Si is Fourier inverse of 1 by Ki, this term here, 1 by Bi here. So now you take the Fourier inverse of 1 by Ki, you can get it as delta t, delta function divided by Ki. How about this one? This one, you look at it. You have j omega here in the term, and you have additional terms here. So that is basically in the Fourier inverse, you'll have an exponential term, exponential of this constant here, sigma k by ki squared, and sigma, so exponential. So you can easily find it out. So basically, you can simplify this expression here, sigma I by ki, 1 by alpha I Ki plus j omega epsilon Ki plus sigma I in this form, sigma I by Ki square epsilon 1 by alpha I epsilon plus j omega plus sigma I by epsilon Ki. So because of this frequency variable omega here with some addition here, you can write this Fourier inverse as exponential minus alpha I by epsilon plus sigma I by Ki epsilon t. So finally, I will express this whole term here as QIT in a very compact notation. So the Fourier inverse of 1 by Si can be expressed as delta t divided by Ki plus QIT, where QIT is this box term here. So we have got the Fourier inverse of the 1 by Si term. So we need to do convolution. So the equation we have, we need to do convolution of the Fourier inverse of the 1 by Si term here. So when you do Fourier inverse, you already got it, Fourier inverse of the 1 by Si term. You have a delta function and you have a Qi term here. So when you do the convolution with delta function, you'll get the exact function itself. So 1 by Ky, Iz by del y, 1 by Kz, Hy by del y. This is with the Fourier convolution with this delta t by Ki term here. We also have this convolution with this Qi term here. So that is the second term, third term, and fourth term here. Qi convolution with del Iz by del y minus Qz convolution with del Iz by del z. Delta term will give you this one and this one. Qi term will give you this one and this one. So, and you also have one term in the right hand side, which is a partial derivative of Ex with respect to time, multiplied by epsilon. We want to find out this third term and fourth term. So this third term and fourth term, we want to find out. We actually want to have a very compact notation of this third term and fourth term, and the notation is called psi. Psi will denote this third term and fourth term in terms of psi. So look at this. We have a notation here. Subscript here Ej means this psi is used for calculating Ex. Then this will be psi Ex. So Ej means this j term will signify why we are using this psi. We are using this psi for calculating Ex here, so it will become psi Ej. If you are using this psi for calculating Ey here, then it will become psi Ey. If you are using this psi for calculating Ez, then this will become psi Ez. So this Ej is actually signifying which electric field component we are calculating, and we are using this kind of psi function here. So psi function here is used for calculating Ej component of the electric field. We also have a W term here. This W term actually signifies that derivative is with respect to W. So for example, in this case, derivative with respect to y, and this will become y here. If it is derivative with respect to z here, then it will become z here. So that is what W is the partial derivative to which term you are doing. You are doing it with respect to x, then it will become del by del x. If it is with respect to y, then del by del y. If with respect to z, del by del z. And you also have n term here, so you are calculating at the nth time instant. T is equal to n delta t. Delta t is the time step size. So the notation is very clear. We have a superscript, we have a subscript. Subscript Ej actually signifies which electric field component we are calculating. W will decide partial derivative is with respect to what. And one more thing is that you also have a K here. This K here, magnetic field K component, you are doing partial derivative. So now looking at this term here, Ex is what we are calculating. So the variable J is X now. Variable J is X now because Ex is what we are calculating from this equation. Then partial derivative is with respect to Y. So the variable W is Y now. Even Q will also have component Y here. So Y, so W is Y in this case, J is X in this case, and what is K here? K here is Z. So you can see that J is not equal to W and not equal to K. So this is the point to be noted. In the equation, we are not having same value of J, of W and K. But W and K can take values X, Y, Z. Ej also can have Ex, Ey, Ez. But you should make sure that J is not equal to W, not equal to K, because that is from the equation we have here. So the notation is clear and the relation between J, W and K is clear. So subscript Ej means Ej is what we are calculating. The W is partial derivative with respect to what? And what component of Q we are doing convolution. N is the nth time instant. K will decide which component of the magnetic field we are doing the partial derivative. Okay. So this is the equation we want to calculate. So let us try to find out. This is convolution anyway, so we have to do convolution of these two functions, QW and del by del W of ISK. So we want to do convolution of these two functions. And you know what is convolution? You need to do shifting and you need to do integration now. So we define a new variable tau and QW tau del ISK by del W and T and delta T minus tau. D tau. This is actually definition of convolution. So you have to do integration from minus infinity to plus infinity, but why we have taken tau is going from 0 to n delta t. That's a discussion we are going to do now. So look at the value of this q function. Q function was exponential function. When tau is less than 0, this q function is not defined. So it's a causal function. We don't have any value of q function before tau is less than 0. So q is equal to 0 for tau is less than 0. So this function, you are multiplying this function and this function, but this function is not having any value below tau less than 0. So at tau is equal to 0 only, it start having some finite value. Before that it was 0. So this will be 0 before tau is less than 0. So in that case, the limit for tau should start actually from 0. How about this function here? This function, look at this function. You have sk and delta t minus tau. So even this function is 0 when this argument is less than 0. It's a causal function. So n delta t minus tau is less than 0, then this function was 0. In that case, sk n delta t minus tau is 0 for you just transfer this tau to the right hand side. What you have is tau is less than greater than n delta t. So this function is 0 when tau is greater than n delta t. That means beyond the value of tau, which is greater than n delta t, this function is 0. Second function is 0. So obviously this integration should actually end at n delta t, because beyond that this function is already 0. So the range of integration is going from tau 0 to tau equal to n delta t. So this is the convolution we are trying to find out, and it is there in the Fdtd update equation. So let us try to find this out. You can define, see, basically your Isk here, magnetic field is discrete in time. So you can define partial derivative of Isk as j going from jmax, del Isk, del omega, and delta t, pjt. Pjt is a pulse function which is non-zero only over the interval j delta t to j plus 1 delta t. Otherwise it's 0. So this is the definition of the partial derivative with respect to w of Isk, because we are doing it in discrete time. So, but in the equation we have here in the convolution, what we have is Isk n delta t minus tau divided by d omega. So we don't have simply Isk t. What we have is Isk n delta t minus tau. So in that case, what are we doing? We are basically flipping and shifting. So tau has become minus tau, then you are adding some shifting term here n delta t. So this is called in the, if you come across your, if you have done courses in DSP and all this, very common. So you actually do flipping. Flipping means sign change, then shifting means you are adding something here. So this function has been flipped and it has been added some uh, term here. So that is called shifting. So what we want to find is basically sk and delta t minus tau. That is, you can get it from here after doing flipping and shifting. So then you can write out the expression for a function after doing flipping and shifting as simply summation j going from n minus 1, 0 to n minus 1, fn minus j pj delta tau. Pj was your pulse function here. F is the function which you have flipped and shifted. Then you can find out this partial derivative with respect to omega of sk and delta t minus tau as summation j going from 0 to n minus 1 del sk n minus j del omega pj tau. So this is what we're getting after we do the flipping and shifting. So let us plug in this value in the expression you have for the convolution. Convolution was going from tau going from 0 to n delta t, and you have q function, q w component of tau. Then you have this function here is the second function. Now we have already got it after flipping and the shifting as summation j going from 0 to n minus 1 del sk n minus j del omega pj tau d tau. And this integration and this summation, you can interchange it. So let us take the summation outside the integration and just do the integration of those terms which are dependent on tau. The tau dependent term are this one and this one. This term is independent of tau. So you can take it outside. Summation j going from 0 to n minus 1 del by del omega of sk n minus j. Integration over this q omega, q wt tau and pj tau. So tau is going from 0 to n delta t. But you remember that this pulse function is non-zero only over the interval j delta t to j plus 1 delta t. So you can just substitute this as 1 over the interval tau going from j delta t to tau going from j plus 1 delta t. Then you do the integration of qw tau. And if you remember this qw tau, it was an exponential function. So exponential function integration is very simple. So you can do the integration now. So let us do the integration of this q w tau d tau over the interval j delta t to j plus 1 delta t. And what was the expression of q w tau? It was an exponential function. Some constant here, then exponential function here. So you do the integration. It's a very simple integration. It would be something like cw bwj, where bw is exponential minus alpha I by epsilon plus sigma I by ki epsilon delta t. And cw is this constant which is defined here. Sigma omega bw minus 1 divided by sigma w kw plus kw square alpha omega. So you can do simple integration. This is exponential integration. We can plug in this value in the previous equation and get the value of psi e j w and at time instant as simply summation j going from 0 to n minus 1 del sk n minus j del omega cw bw to the power j. And you can also separate the terms. See, j is going from 0 to n minus 1. You can separate the term j is equal to 0 and j is going from 1 to n minus 1. So when j becomes 0, this term will become 1. So you simply have this term and c omega. So cw del sk n divided by del omega. Even j is 0 here, so n minus j will become simply n here. So cw del sk n divided by del omega plus all other remaining terms, j going from n j1 to n minus 1 del sk n minus j divided by del omega cw bw to the power j. Let us put a new variable j is equal to l plus 1. Then we can express this right hand side term in terms of l variable. So first term remains the same. Second term, since we have put j is equal to l plus 1, it will be summation L going from 0 to n minus 2 del sk n minus L minus 1 divided by del omega cw bw L plus 1. We are actually trying to simplify this term. You'll see later on that this will become a very simple term. Okay, so let us take out bw common factor in the second term. In this second term, we just take out a common of bw. When we take out a common of bw, what we have is simply summation L going from 0 to n minus 1 del sk n minus 1 minus L divided by del omega cw bw L. So this is the first term, this is the second term, and looking at this term here inside the second bracket, this looks exactly like psi n minus 1 ejw. So that's the simplification we want to do it so that we can write an update equation of psi ejwn. So psi ejwn turns out to be equal to this first term here, cw del skn divided by del omega del w plus bw psi n minus 1 ejw. So this is basically the update equation for psi ejwn. Let us come back to the equation we have. This was the equation. You have this partial derivative with respect to time of ex with respect to time multiplied by epsilon. This first term, second term, and third term and fourth term, we have actually denoted it by psi ej. This term will become psi ej yn. This term will become psi ej zn. So these are psi ej yn and psi ej zn. So we can write the update equation now. Update equation, look at the left-hand side. This is very simple update equation for the electric field with respect to time, partial derivative of electric field with respect to time. So epsilon del Ex by del T equal to, you can write the update equation as Ex. Ex is always calculated at the center of the edges along the x-axis, half at the center of the edges along the x-axis. So half I plus half j comma k, I plus half j comma k. This is a time derivative. So n plus 1 to n divided by delta t. Right hand side, this is partial derivative of iz with respect to y. iz is located at the center of the faces along the xy. So it will be I plus half j plus half k. I plus half j minus half k, because we are doing partial derivative with respect to y divided by delta y. And magnetic field is calculated at the half integer time step n plus half n plus half. Similarly, also n plus half n plus half. xy is located at the center in the xz plane. So I plus half k plus half j. I plus half j k minus half, because we are doing partial derivative with respect to delta z. This is your psi ex y. I plus half j comma j, psi ex z, I plus half j comma j. So this psi is calculated with respect to ex. Ex is also always calculated at I plus half j k, I plus half j k. So that's why this space location. Time is at n plus half, n plus half. So how do I calculate this term and this term? So we can do it from the update equation we have derived today. So we have that update equation, psi ejwn is equal to bw psi ejwn minus 1 plus cw del skn by del omega. This is a long derivation we have done today. So you can find out psi exy at I plus half comma jk at n plus half is equal to by psi exy I plus half j comma k n minus half plus cy iz n plus half I plus half j plus half k, partial derivative with respect to y, so I plus half j minus half k divided by delta y at n plus half times 10. Similarly, you can also find out psi exz at I plus half j comma k at n plus half times 10 as bz psi exz I plus half j comma k at n minus half time. Then constant cz isy at n plus half partial derivative with respect to z, that's why I plus half j comma k plus half I plus half j comma k minus half. So everything makes sense here. So what are these constant here? We have defined bw was exponential minus alpha I by epsilon plus sigma I by ki epsilon delta t. C omega was sigma, cw was sigma w minus bw minus 1 divided by sigma w kw plus kw square alpha w. So these are material dependent parameters. So that's all about the Fdtd program. So the Fdtd program we have just considered was called convolutional PML. No, convolutional PML. It works quite well for the low frequency also, and I think it's supposed to be one of the best PML there which is existing today. So convolutional PML, CPML. So that will actually conclude the discussion on PML, and we have one more very interesting topic which is called unconditionally stable Fdtd. So you have seen that till now when I take the time step size, I have to follow the current stability criteria. So I cannot take my time step size delta t arbitrarily. If I keep on increasing it, the FDTD is going to become unstable. But if I keep on increasing it, delta t step size, the time it takes for the simulation will reduce. Because every time step, if you keep on increasing it, the simulation time is going to decrease. So I want to have a highly efficient FDTD which should be able to simulate even the very last structure like aeroplanes, rockets. But when I increase the step size, time step size, I cannot do it because FDTD become unstable. But there are new kinds of FDTD. This is one of the latest area of research in the FDTD, which is called unconditionally stable FDTD. So this kind of FDTD is not bound by the current stability criteria. This is beyond the current stability criteria. You can take delta t size arbitrarily large so that your simulation time will become very small. So time step size can be chosen beyond the current stability criteria limit. There are many types of FDTD here. We'll discuss some of them. The first one is called the Crank-Nicholson FDTD. This is actually proposed by this person here. And this is also one of the unconditionally stable FDTD. So here, basically in the Crank-Nicholson CN FDTD, the time and space derivatives are discretized by center finite difference approximation. Fields affected by the curl operations are averaged in time. We'll see what does this mean in the next slide. Just before that, we have 6 equations, 3 for first Maxwell curl equation, 3 for second Maxwell curl equations. Can I convert these equations into a matrix equation? So you can see here in the left hand side, this we have 3 components of the electric field, 3 components of magnetic field. We are doing partial derivative with respect to time. So can I write something like del u by del t, where u becomes ex, ey, ez, sx, sy, az. I can definitely do that. In the right hand side also, if you look at the fields, you have 3 components of magnetic field, Ix, Sy, Z, and 3 components of electric field. All these combinations are 3 components of electric field and 3 components of the magnetic field you have in the right hand side. And if you define a matrix A and B in a very proper way and multiply with Ex, Ey, Ez, Ix, Sy, Z, which was U matrix, then you should be able to write this whole equation in a very compact equation in a matrix form. So how do I do it? I define a matrix U here, Ex, Ey, Ez, Ix, Sy, Z, and I define another matrix A here, which has components like 1 by epsilon del by del y, 1 by epsilon del by del z, and so on. Similarly, I also define another matrix B, which has component like minus 1 by epsilon del by del z. So when I add these two and multiply with the U, then I will get the right hand side of the Maxwell equations. So the Maxwell equation can be very compactly represented in a matrix form like this. Del u by del t is equal to AU plus BU. A and B is already defined. We have defined it. U is also defined. So now, what do I do in the CN FDTD? So in the CN FDTD, this partial derivative with respect to time, you can simply write as UN plus 1 minus UN by delta t. We do one thing more in the CN FDTD. So right hand side, we have A plus B U. So in the CN FDTD, this U here is actually taken as the average of the UN plus 1 divided plus UN divided by 2. So this is what we do in the CN FDTD technique. Right hand side U is actually taken average. Field affected by the curl operators are average in time. So this side, whatever fields affected by the curl operation in the Maxwell curl equations are actually average in time. That is UN plus 1 plus UN divided by 2. So let us try to simplify this equation. So we rearrange the term. So UN plus 1, we have just taken delta t to the right hand side. So UN plus 1 minus UN is equal to delta t by 2, A plus delta t by 2, B, UN plus 1 plus UN. So we have just taken delta t here to the right hand side. We can combine terms, UN plus 1 terms in the left hand side. We bring all the UN plus 1 terms in the left hand side, bring all the UN term in the right hand side. Finally, what we have is something like this. So you can simplify it as this, the identity matrix minus delta t by 2A minus delta t by 2B UN plus 1. Right hand side, what we have is identity matrix plus delta t by 2A plus delta t by 2B UN. So now I want to simplify these equations. We have right hand side and left hand side. I want to bring it in the form something like this. If I have something like 1 plus minus a1 into 1 plus minus a2, I simply get 1 plus minus a1, 1 plus plus minus a2 plus minus a1 a2. So I want to bring it in this form. So I need to have something like a1 and a2 here. So what do? I actually add a term delta t square a b by 4 on both sides. I add this delta t square by a by 4 in this side, then it should also be added in this side. I also add delta t square a by 4 un, then I should also subtract delta t square a b by 4 minus un. So I can add and subtract the same term on one side, or I can add the same term on both sides. So it doesn't make any difference. It's the same equation, but then we can bring this equation in the form we always wanted. So this term here, you can write it on the form I minus delta t by a 2a, I minus delta t by 2b un plus 1. This right hand side term also I can express this term here, I plus delta t by 2a, I plus delta t by 2b un. Then you have this additional term here, delta t square by 4 ab un plus 1 minus un. So we have expressed in this form here. So now there is something called ADI Fdtd, alternating direction implicit Fdtd. So in that alternating direction implicit Fdtd, which is unconditionally stable Fdtd, we actually neglect this last term here. This last term, if we neglect it also, the error is not much, because this is delta t square by 2. So this is one order higher than this term here, this term here. So we actually neglect this term here. So we simply have this equation in the left side and right hand side. And in the ADI Fdtd, we split this into two steps. So in the usual Fdtd, what do? You actually find out, let's say u at nth time instant, then you actually find out u at n plus 1 time instant. But here, what we'll do this in two steps. We'll first find out un from un plus half. From un plus half, we'll find out un plus 1. So this is a two-step procedure. From n to n plus half to n. So looking at the previous equation, we have this term, this term, this term, this term, and this term here, this term here. I can actually split the Fdtd of that equation into two parts. First is I go from un to un plus half. I multiply I plus delta t by 2b with un, and I will try to get un plus half. And we also have this I minus delta t by 2a here. And from un plus half, I have found out from the first step. In the second step, I actually find out un plus 1. So un plus 1, un plus half, I plus delta t by 2a is equal to un plus 1, I minus delta t by 2b. So this is a two-step process. This half step, this half step, it will become a full step. So the ADI Fdtd, because of this neglecting the second term, which is delta t squared by 4, we have the computational overhead is smaller. That means you can actually do the simulation very fast. And because of this neglecting the higher order terms, there is some also accuracy, accuracy is not so good. Okay, anyway, so let us go to the ADI Fdtd for the this was the Maxwell equation. We have three equations for the electric field and three equations for the magnetic field. So now ADI Fdtd is a two-step scheme. We have a first procedure and we have second procedure. So in the literature, they call this first step update for the Fdtd is called first procedure, and second half step update equation is called the second procedure. So how do we do that? Let us consider the simple case of 2D TMZ problem. In the 2D TMZ problem, magnetic field doesn't have any Z component. So in that case, magnetic field have X and XY, X and Y. And electric field is perpendicular to magnetic field. Electric field will have only EZ component. So from the 6th Maxwell equation, it will reduce to only 3 equations here. These are the time-varying terms. These are space dependent space derivatives on the right hand side. So for 2D TMZ problem, we just have three equations. So how do I use ADI Fdtd for the 2D TMZ problem? So ADI means alternating direction implicit Fdtd. This is an unconditionally stable Fdtd. How do I write the update equation? So first procedure means we are doing updating from the n to n plus half. So this is the equation. We want to do the first procedure for del Ez by del t is equal to 1 by epsilon del xy by del x is equal to minus del xx by del y. So how do I do it? Fdtd update equation. Usual stuff. So I calculate Ez at n plus half at location I comma j is equal to Ez at n I comma j. So this is the Ez of the previous time instant. So if I want to find Ez at n plus half time instant, I need the Ez of the previous time instant at the same location. Then you have these terms here which are dependent on the xy and xx. So when you do partial derivative of xy with respect to x, xy is calculated at the center of the faces in the xz plane. So I plus half. So this is partial derivative with respect to x. So I plus half, comma j, and I. So you will have terms like so multiple is calculated at n plus half times 10. So you'll have terms like xy I plus half comma j, and you'll also have terms like xy I minus half j n plus half. At the same, basically partial derivative with respect to x. So x is I plus half comma j I minus half comma j. So this is actually in the 2D case. So 2D case, your magnetic field was circulating. So I was telling you about the 3D case, but this is a 2D case. So you have to remember the master diagram. So electric field was calculated at the center of the solution. So if you consider a point here, then magnetic field was circulating around this. So you remember that master diagram. Center is electric field. Electric field is calculated at the integer space steps I and j. Magnetic fields are calculated at the half integer space step, but this is y. Y, then corresponding running index is j. This will be integer. The remaining running index will be non-integer. So you have I plus half, I minus half j divided by delta x. So this is a partial derivative with respect to x. This is partial derivative with respect to y. So now x. So the running index for x is I. So I will be integer. So I j plus half I comma j minus half divided by delta y. So that is the update equation you have for the del Ez by del t. But then look at this term here. These terms you calculate at the n plus half, but here on the left hand side also you have n plus half. So basically most of the time what we have done was, if we have n plus half here, on the right hand side we'll have n or n minus half. But here in the implicit Fdtd, whatever Fdtd we have considered till now was called explicit Fdtd. In the implicit Fdtd, on the left side and right side you have the same time index for the electric field and magnetic field. So here also you are calculating electric field at n plus half. Here also you are calculating magnetic field at n plus half. So this is implicit Fdtd. So you do not know the value of n plus half value of the magnetic field at that particular same time instant. So how do you take care of this kind of term here? So that is, you use the third equation. The third equation is del xy by del t is equal to 1 by mu del Ez by del x. Third equation, you can simplify it, del xy by del t. So xy is basically, so the running index for y is j, so j would be integer, the other one will be half integer, I plus half j. So xy at n plus half, xy at n, partial derivative respect to time divided by delta t. You take delta t to the right hand side. Then what is this? This is the partial derivative with respect to x. Ez is calculated at the integer space step. So I plus 1 comma j, I plus I comma j, partial derivative with respect to x, so delta x. So this is the update equation for this third equation of the TMZ problem. You have 2D TMZ problem. So now you know the value of xy at n plus half. That is what we wanted to use in the previous equation. We do not know the value of xy at n plus half. Xy at n plus half at location I plus half comma j, I minus half comma j. But we can use this third equation and plug it in the first equation. So finally what we have is, we have replaced xy at n plus half, I plus half, comma j, and xy at n plus half, I minus half, comma j. You can replace it from this. Previous slide we have done the derivation. You can plug it in here. This is what you have here, you have here. Then after that you can combine terms, bring all the terms. See here you have terms like n plus half, n plus half, n plus half, n plus half. All the n plus half term is the latest time instant term. You can take it to the left hand side. All the nth instant term you can keep it in the right hand side. It is nth term, nth term, nth term, nth term. At the nth time instant you can put it in the right hand side. Then you can write it in a very compact equation like alpha 1 z I minus 1 comma j n plus half plus beta 1 z I comma j n plus half plus gamma 1 z I plus 1 comma j n plus half. So what you can observe here is that this constant alpha 1, beta 1 and gamma 1 are different. Alpha 1 is defined like this, minus delta t by 2 mu delta x, delta t by 2 epsilon delta x. These are material dependent parameters. Beta 1 is 1 minus alpha 1 gamma 1. So alpha 1 was material dependent parameter. Similarly, beta 1 will also be a material dependent parameter. Even gamma 1 is also material dependent parameter. Minus delta t by 2 mu sigma x, delta t by 2 epsilon delta x. So alpha 1, beta 1 and gamma 1 are material dependent parameters. So what you observe is here is that this time instant n plus half, n plus half, n plus half, but space locations are different. Ez is calculated at I minus 1 comma j. Ez is calculated at I comma j. Ez is calculated at I plus 1 j. So that is what you need to note down here. The location, space location of Ez is different for first term, second term, and third term. Alpha 1, beta 1, and gamma 1 are already defined here. They are different material parameters which should be multiplied with Ez at I minus 1 comma j and Ez at I comma j and Ez at I plus 1 j. Right hand side you have all the terms which are dependent on the nth time instant. We'll just denote it by something like R1 n, R1 n. We'll just denote this whole term by R1 n. Then we can write in a matrix equation like this. So we have beta 1, 1, gamma 1, 1. So what is 1 here? See, you have I minus 1, I, and I plus 1. So now, if I start with I is equal to 1, this will become 0 here. If I start with the first row is I is equal to 1. First row is I equal to 1. You multiply this first row and this column here, you get R1 and 1. That is for I is equal to 1. But I is equal to 1, I minus 1 will become 0. This term will not be existing for the first row because we cannot have any value of 0 here. So we should start always from 1. So when I is equal to 1, this term is 0, but this term is still there. This term is also there. So that's what we are doing. Beta 1, gamma 1 multiplying with Ez at n plus half at j comma 1 and Ez at n plus half j comma 2. When we multiply this, we will be getting R1 and 1. Similarly, you go to the second case when I becomes 2. I becomes 2, then 2 minus 1 is 1 here. So you have Ez1 here. You have Ez2 here, you have Ez3 here. So that is your Ez1, Ez2, Ez3 here. You also have alpha 1, beta 1, gamma 1 for the I is equal to 2. So alpha 1, 2, beta 1, 2, gamma 1, 2. Multiply with this, what you get in the right hand side is R1 and 2. Similarly, you'll also have 3 terms for all the terms except the last one. Look at the last one when your I becomes n. So n minus 1 is existing. So n will also exist, but n plus 1 will not be existing because this is outside the solution space. So we'll simply have alpha 1 m, beta 1 m multiplying with Ez at m minus 1 and Ez at m. We don't have Ez at m plus 1. So we will have only 2 terms here. Then finally that will be equal to R1 n at m. So this equation we need to solve in the ADI Fdtd. How do you solve it? Just before that, let's go to the second procedure also. In the second procedure, you need to update from n plus half to n plus 1. First procedure is n to n plus half. Second procedure is n plus half to n plus 1. So this is the update equation like last time. Electric field is calculated at the integer space step I comma j, I comma j. So this is the I comma j Ez at n plus 1 and Ez at n plus half. Previous time instant. You do partial derivative of xy with respect to x. xy, so this is a 2D case. Look at the master diagram. Y running index is j, so it will be integer. The remaining running index will be half integer. Partial derivative with respect to y, so I plus half minus I minus half divided by partial derivative with respect to a, I plus half, I minus half divided by delta x. Then again this one, del x by del y, partial derivative with respect to y. What is the running index for x? X is I will be integer, remaining one will be non-integer, half integer, j plus half, j minus half divided by delta y. But then the problem is that this term here and this term here, they are at the same time instant. So left side you have n plus 1 time instant, here also n plus 1 time instant and plus 1 time instant. So this is implicit Fdtd. You want to calculate electric field at n plus 1 time instant, but you are using magnetic field at the n plus 1 time instant at the same time instant. But in the previous Fdtd, we have considered explicit Fdtd. This should always be for the previous time instant. So how do we take care of that like last time? So use the second equation. Second equation is del x by del t is equal to minus 1 by mu del Ez by del y. So let us try to write the update equation for this. X, what is the running index? Running index for x is I would be positive, but j would be, I would be integer, but j would be half integer. I, j, comma, j plus half, I, j plus half. Partial derivative respect to time, so n plus 1 to n plus half divided by delta t by 2, because we are considering only half integer times that. So you take delta t by 2 to the right hand side, so delta t by 2 divided by mu delta y. Delta y is partial derivative respect to y. Ez is calculated as integer space step, so Ez I j plus comma j plus 1 Ez I comma j divided by delta y partial derivative. So use this equation and plug it in this term here, then you'll get the equation. So you plug it in the right hand side, the two terms which are implicit, this last and last but second term, and you combine the terms like last time. So alpha 2 Ez I comma j minus 1 plus beta 2 Ez I comma j gamma 2 Ez I comma j plus 1. So here this electric field are all at the same time instant, n plus 1, n plus 1, n plus 1. But then this space location, no? One is j minus 1, j, another is j plus 1. Right hand side, we are calculating electric field and magnetic field at the previous time instant, which are n plus half everywhere. We just call it as, let's say, R1n or something like that, like last time. What is alpha 2, beta 2, and gamma 2? They are not same with that of the previous first procedure. This was the second procedure. Alpha 2 is minus delta t by 2 mu delta x, delta t by 2 epsilon delta x. Beta 2 is 1 minus alpha 2, gamma 2 is minus delta t by 2 mu delta x, delta t by 2 epsilon delta x. So we have alpha 2, beta 2, gamma 2, which are material dependent parameter, Ez at different locations, j minus 1, j and j plus 1. You can write the tridiagonal equation for the ADI Fdtd for the second procedure. Like last time, first row and the last row will have only two components here, beta 1 and gamma 1, alpha 1 and beta 1. All other rows will have three components here. This is the Ez at 1, 2, 3 and up to m, and this is R1, 1, R1, 2, R1, m. Okay, so we have tridiagonal equation in both the first procedure and second procedure. What is a tridiagonal equation? Tridiagonal equation is a equation in which you have a tridiagonal matrix. This is a diagonal element. This is one lower and this is one upper. So any matrix which has these three lines filled off, all other lines are zeros, are called tridiagonal matrix. And it is very easy to solve this kind of tridiagonal matrix. Let us consider this 4 by 4 tridiagonal matrix and try to illustrate how to find inverse of this matrix, because we need to do inverse of this matrix. Look at this. For example, if I want to solve this Ez, then I take the inverse of this, multiply with this R matrix here. So I need to take the inverse of this matrix here to find out Ez. Ez is the noun. I want to find Ez, then I take the inverse of this, multiply with the R matrix. So how do I take the inverse of this tridiagonal matrix? It's very simple. You have to make this tridiagonal matrix upper triangular and do backward substitution. So the simple matrix technique, you want to make this tridiagonal matrix upper triangular. What do? You multiply with A2 1 by A1 1 with the first row and subtract it from the second row. Then this first term will become 0, second term will become like this, third term remains same, and so on. So we have already made this term 0. Similarly, you can also do it. You multiply the first row with some quotient, then make sure that this is 0, and so on. You can do that. That's a simple method you usually do in matrix calculation. If you want to make the matrix upper triangular, you will have to make all these terms 0 below the diagonal matrix. You can do that. You continue that, and so finally we'll make an upper triangular matrix which looks like this. All the lower triangular matrix elements have become 0. So now how do I solve this kind of matrix? That's also very simple. Look at the last term here. You multiply this last fourth row with this matrix, this vector here. What you get is A4 4 X4 is equal to B4. Then what is X4? X4 is B4 by A4 4. So from this last row you can get X4. And look at this third row here. Multiply this third row with this vector here. What you get is A3 3 X3 plus A3 4 X4 is equal to B3. But here, the only unknown you have here is X3. You already know what is X4 from the previous operation we have done. So we have X4. So you can just plug in X4 from this value and you can find out what is X3. So X3 will be simply B3 minus A34 X4 divided by A33. So now once we know X4, we can find out X3. X4 is already found out. Similarly, second row you multiply with this, what you have is A22 X2, A23 X3 is equal to B2. From there you can find out X2. X2 is B2 minus A23 X3 divided by A22. But I already know X3 from the previous operation. So this is called backward substitution. So you can write a small MATLAB program and do the inverse of a tridiagonal matrix. I have done that. You can also do it. I think we should stop here.